Well, Marcus was here during, I think it was last year in the summer?
Yeah.
Marcus was here for 5 weeks doing some supercomputer things, and we were doing some wavefield testing. And the idea came up to see what would happen if we took our wavefield and basically doubled it, put a second array on top of it upside down, and then offset it by one driver, making it, what is that, 2.5 centimeters now?
A little bit more because you're W shape, but
yeah. So
3
centimeters or so. So basically taking the resolution of the system, and in theory, the frequency range in which the localization effect can be perceived, increasing that. And so we tried it out. The system was not designed to do this. This was not a thing that we necessarily accounted for. And Marcus sort of roughed out everything on this is like a little bit rough in a thing that precision is the key part. So I'm giving all of these caveats because this is the kind of thing where this is stuff that we're just thinking about now. Marcus and I were talking about it. We're not necessarily sure that this is the highest density array that exists. It's definitely the highest density one that you've worked on.
The highest density I worked on, but maybe there are some others which have higher density.
Yeah.
I don't know all the arrays which are hanging around in the world. Would be nice, but.
Yeah.
So we tried to set this up very quickly because you see and you feel it's a very dense program we have. And so with the concert yesterday, and to be honest, I was too tired of the concert to set something up. And so we came here now in between the talk, and the first question was, oh my God, we couldn't remember if we shifted the second array to the left or to the right. So that's a little problems you face. But that's saying, so normally what I was saying yesterday, when you do a high density array, precision gets very important, because when you deal with high frequency, then the distance in between the drivers or the actual driver position matches. When it doesn't match the computed driver position or the filter for the driver position, then you get artifacts in your system. So this is a very quick, I would call it sketch or try to at least let you understand what happens if you use every fourth speaker, every second speaker, every speaker from the array below, and then on top of it to reduce it even to half of the size which you normally have with the array, which you learn to listen in some listening sessions and whatever, better to know. So it sounds a little blurry because, that comes from the effect that we didn't manufacture it properly. But it gives you, I guess, still the feeling what happens when you reduce the size and you get from 3 kilohertz to 6 kilohertz for the wavefield synthesis, which makes, in my opinion, a lot of sense. It makes, maybe, I was a little bit more impressed because the array last year was in the concert hall. And so we had a very long, so we could go far away from the array just to listen it, like doing a 16-channel recording on the stage, and then swapping in between the half density or full density or highest density, however you want to call it, and the normal array. This was just impressive, because the clarity you gain when the source gets from blurry big to small in a huge orchestra recording, it's really impressive. And I think that's something you can sense. You heard yesterday Natasha's piece. It's not topology timbre. I have to look up the title, sorry.
Momentary. Being momentary.
Pockets? No.
Invisible being.
Being whatever. You have the program, sorry. So she was sending me the file a couple of days ago because we planned to play another piece of her. She was saying, hey, you have 64 speakers, and that's a piece which was produced in 7th order. So it's perfect for the array you have. And that's something you can hear, and what you can hear when you hear the first movements in this piece, so the grains going around, it's the clarity. It's opening up, and that's very impressive when you go from low order in ambisonics, for example, to higher and higher order, or the increase when you have very many sources, is the clarity. Everything becomes open and clear. And so, we hope that we can demonstrate with the WFS that it makes sense to use high-density arrays or very high-density arrays. Let's try it out.
That's right. So, because Bobby mentioned this, so we're on the bottom array here, the far two boxes, we're not using those. So visually ignore those. So we're using the lower array is just 4 boxes, and then the double array is 8 boxes stacked on top of each other. So these don't matter so much. And then I think, are we going to do the octet? Is that what we're going to use? Sorry.
I don't know. We didn't agree.
I mean, it's short. I mean, that's fine with me.
Yes, let's do that one.
So this is, we talked about the string quartet that we've done, and one of the things we've been doing here is just basically trying to keep upping the number of sources, and then seeing sort of what we do, and then also seeing how different instruments react. You know, the pressure-based instruments like string instruments versus wind instruments, and how they each versus voices, so on and so forth, just to see how they all react when sort of are being synthetically recreated through the wave field. And so this is a Mozart Wind Octet that we recorded with the Trueleaf. It was like, if you imagine, you could just get like the best ensembles to do things. It's a New York City-based Orpheus ensemble who are extremely good, and they were generous and came here and recorded this octet with that. So we're going to use that as our source today. Yeah, and so you should be able to follow along here on the bottom there, and you'll see every fourth, every second, every speaker, and then there's lower spacing and then full array. And so we're basically going to start moving through those things and see if you feel the images start to resolve higher. We're actually very curious what your perceptual experience is of this. And then I believe the objects are somewhere, ignore the tape on the floor, they're somewhere around here, in this area-ish here. So if once we've sort of gone through that, you can also sort of feel the definition of the object itself is actually what I perceive the most, the edges of it, which is a really strange thing to say, and how those edges suddenly fall off or smooth. I don't know, it's a little weird. But let's see what happens, yeah?
So let's go do a... So I don't know if you heard any difference because I'm sitting in the phasing part of the show. So I just hear phasing artifacts in my ears all the time, which drives me a little bit crazy. So this was the low array playing, just playing every fourth speaker, every second speaker, and then every speaker. So you reduce the size, and especially with focus sound sources, that's a huge difference because focus sound sources, when you're too far, the speaker spacing is too large, then they fall apart. So, yeah, I rely on your feedback because I'm in the phasing part.
The problem is level also when you're switching from one.
Yeah, this is, it's not very well set up because we didn't compensate for the level. Sorry for that one. It will be better with the full array and just having the lower part and then the high resolution array up and running. But I hope you got the blur actually, which is the most important part. That you see that the sound source, which might be that big with every fourth speaker, gets narrower and narrower. And then this was the idea because this was our first test in the concert hall. I said, hey, because there's always the question, I like doing high density speaker arrays, but you ask yourself the question, okay, now we're up to 700. Does it make sense to go higher and higher and higher? Because if it doesn't make sense, On paper, yes, but perceptually, does it make sense? And so we came up and saw clearly, which was clear, since we have a 16 centimeter spacing array, so every second speak is very close to what we have at IRCAM. Then it makes sense to get even denser for high frequencies. And then we've been saying, okay, now we are playing every speaker. It would be cool to further reduce it as far as we can. So we've been putting on top of the low array a second array, which it doesn't reduce it by half of the size because we have a W-shaped speaker array now. But anyway, we get closer with the speaker. So I will now do the same thing and just swap in between the only lower part of the array and then the full resolution array. Sorry. So now from the full, something's really vibrating there. Just give me a second. Something's really not sounding that good.
The buzzing is on the back of the,
Ah, okay.
it's a little box. I can't
Okay.
fix that.
Maybe we do the quartet, the tango again,
Yeah.
because it's a recording which I know better.
Llegabas por el sendero delantal y trenzas sueltas brillaban tus
So that's the lower part of the array playing.
claridad de luna llena. Mis labios te hicieron daño al besar tu boca fresca. Castigo me dio tu mano, pero más golpeó tu ausencia. Volví
Now I'll go
por
back.
caminos blancos, volví sin poder.
And here you hear with the voice, at least from my position, because I was putting it a little bit closer that I understand what I'm doing and I can hear it. But you can clearly hear it goes from bigger to very defined in space. And it's be going from, yeah, so in the W shape, we are not half the speaker size, but, so this was the reason for us to say it makes sense to go even higher than the spacing we have here. And then it's an engineering question, maybe to manufacture, so, sorry. Stop this while talking. And then it's just an engine, so just Jens will talk maybe a lot about engineering questions, building a microphone array. So when I say it's just an engineering question, it means a lot of time, or spending a lot of time in all these problems. So did you all hear it? Was it clear? Because as I'm saying, I'm here in a not very preferred position. So are there any questions so far?
So the last segment you played had the most.
The highest resolution,
Okay.
yeah. And then I was going back because then you hear actually from, I don't know why when you go higher and higher, it's perceptually less impressive than when you get used to the small tiny source which you can produce with a very high density array. and then you go one step back, it blows my mind, and I don't understand why it doesn't work in the other direction. So it works as well, but you get so used to this clarity you have, and then you step back, and then it's just, wow, and it's the same thing you're doing. I'm just getting from the double resolution or highest resolution array to the next lower one. So I don't know what your...
Actually, could you do that again? Could you just like switch back and forth between them a couple times?
Yeah.
So how
Yeah.
far away do you have to be before you eliminate the problem with the near field issue you deal with? How far back do you have to be before the phasing starts to dissipate from the line?
It depends where the source is, actually. So when I look, so we are not using the full array, we are stopping here. When I now look at this source here, and I take the extremes, like this and this, so this would be the area. When I put it very far away, then all the people who are outside this area would be in the phasing zone. So I just move it around, and then you can maybe get it better. But I use the guitar.
The higher resolution should also increase the clarity for non-focused sources as well, right?
Yes, sure. But it's just, with a focus sound source, when it was more for demonstrating when you go from every speaker to every second, every fourth speaker, that it falls apart, because there's a distance where a focus source doesn't make sense, as you know, because you've been using our side arrays, which have a 30 centimeter spacing. The focus source still works somehow, but it's not as precise as with a 16 centimeter or lower array. So that's why I was using focus sources. But of course, it increases the frequency range where you physically correctly reproduce the sound field is the same for the sound sources behind the array. Sure. The head is, let's see, that's 9 meter distance, I guess. 1, 2, 3, 4, so that's 1, 2, 3 meters. So that's 1, 2, 4, 5. No, it's more.
I think it's a 15-meter filter.
15-meter filter set. So the head would be at 50-meter distance as indicator. So it's in the other room. But it doesn't. So it's just a visual thing, you know. But so you would be more here, I would say. So let's see. Raise your hand when the sound comes to you, and then we'll see how far away you are.
Maybe it makes sense to do just one source.
Yeah, I just do one source. Yeah. Somebody got the source? And then as far I'm away of the array, so the first rows will now be in the phasing more or less. So where I am? Yeah, still 2 rows to go.
Why does it jump? It kind of jumps.
Because you are now outside this zone, and I quickly explain you why you get this feeling that it jumps when it's really before you. Okay, just a second, because I think I got the last row as well now. Okay, so I'm going back here. And I stop it here. Yes, so first question was why it jumps. Imagine that when I'm far away from the array, so it gets narrower. So the most impressive part is, of course, when the source is here. So you have so it's like sticking your head. But when it's here, you you quickly, so here in the phasing zone, you get into the suite area and you're away from the phasing zone. That's why the impression is that it swipes away. If it's a little bit in front of you, it's way better because here you're in the phasing zone, out of phasing. The closer I get to the array, or the longer the array is, you know? When the array is a very large array, so if it would just be the extremes of the room, then for this row here, I would have a suite area, which is like this. So you get a very nice function when I go away, so you don't have this effect that it jumps.
If you have an array on the back, it will work symmetrically?
It would be the same, but then, you know, when the source is focused from the array in the back, then those people will be in the phasing zone of the back array. And when it's focused from the frontal array, those people will be in the phasing zone of the frontal array. So that's, yeah, but they can work together. But even you always will be inside or outside of phasing zone. That's what I was talking on Monday about. If, like, I was tracking myself, and so I choose the parts of the array which work best for me. I'm very egoistic. And then I can have this effect to have an object in front of me, a sonic object. Because then I use always the arrays when I have ones around the audience array, then I always use the parts of the array which work perfectly for me so that I'm always in the suite area. So I walk around the object and actually my sound rendering follows me. So this is beautiful. But yeah, it works for one person and you need a once around the audience array. But, you know.
For more than one person, if you have multiple ways of tracking, like
No,
face recognition.
because when I introduce a second person, which is another perspective, then he or she would put me in the phasing zone for the objects for her, so it doesn't work. That's a huge problem we face, as we've been talking about in cave applications and whatever. So it works for one person. It's the same with a stereoscopic screen in a cave application. So it works for the person with the tracker, which gets the nice rendering done. But if there's a second person, it doesn't work anymore.
Can you just,
Yeah, first here.
So my understanding is the idea of head shadow is kind of creates this phase effect. Is that
The idea of?
the head shadow, like our head actually shadowing?
No, the phasing effect comes just, you've seen the simulation, so I have to wait until these wavelets here come. So all the wavelets which come together form the source here.
Yeah.
But at this position, they haven't yet formed the source. So I just got hundreds of wavelets going through my head, and the phase relation of these wavelets do not make sense because they only make sense in this position in the room. And from here on, they form the wavefront, and then it's traveling correctly in space. So when I'm in between the array and the source, I just hear this wavelet phasing. Okay? Okay? Yes, please.
So, what would the intersection of the zones be like? Is it, I mean, I imagine it'd be small, but could you just have a concert where everybody is in the intersection of the cones that you described, and then?
So, actually, just imagine you want to do just synthesize an object which flies through the audience. Okay. This just doesn't work. Okay. So I can, as we've done the concert last year with Benny Solution, situation like here in the concert hall, and we had a very long array behind the stage, and then virtual trombone players from the perspective of the audience rather close to the array, so like somebody's being on stage, so 2 meter distance or whatever from the array. So it worked for all the audience because everybody, so we've been choosing like, okay, no, nearby all the audience is in the suite area. If I then would have moved the virtual trombone players closer, then it falls apart because they get far away from the array. And so we had this discussion with Bobby because he was working on the theater piece with Andrew Schneider and was saying, hey, but I want to move a sound object which goes through the heads of the audience. And so we came up with the idea, which he will present later on. So, okay, so now we focus the sound source from the ceiling down. So the sound source, the suite area is here. And here it's a cone like this. And so it moves like this. And this, you'll see it. That's your part of the show. But with all this technology we have, so this was also one of the questions you heard about the Cosima project, or what Gus was presenting about his project, to bring sound closer to the people. So the easiest way to do so is to use a speaker which is close to them. Because all the other technologies we have, like time reversal mirroring, which uses also inverse traveling waves which superimpose in one position in space, you always have to wait until they come. And then the source appears. Of course, I once did a sound installation where I was using reversed time reversal mirroring, which is a little somehow close to what we do with wave field synthesis for the focused sound source. And to get rid of these artifacts which you hear, I was putting like a sea of white noise, so slightly modulating white noise. So you get into a room and you hear white noise, or pink noise modulated. So you hear, and then you come to a point where there's a little tiny point source which is talking to you, which is beautiful because all the artifacts are masked out. Your brain is working nicely because you always create your stable work. You don't hear the phasing, or the phasing is lost in the sea of pink noise. And then you come to this point where there's this little source just talking to you. And it's a very strange moment. It's so, especially when it was working for the first time, you walk and then, oh, cool. But if you switch off the white noise, it's just annoying. Because then you hear, before you go there, you hear, and then you hear the voice and you go away. That's not so beautiful.
I was wondering if you could cancel with the time reversal mirroring the sea of noise before it focuses at the point. And you're saying you use white noise and that works to mask. Can you also actively cancel it?
Yes, this, you can actively cancel, you can create silent zones.
Is that very computational? Is that easy?
The problem is it's very limited in the zone which you can do it, because you project actually, so your control problem to the outskirts, to the boundary. So just imagine that the wavefront doesn't stop here, it just goes on. So two wavefronts come here and they superimpose or they cancel each other out. But here, they might superimpose with the phase relation. So you have twice the amplitude. So I need a third one which is coming from here, canceling out here, but it might create an artifact there. So you have to solve the wave equation for the entire zone, which you normally do with optimization theory, with Lagrange multipliers. And then you get driving functions, which allow you to create a silent zone, and so we call it a bright zone and dark zones in a room. So it's working in practice. You need, first of all, very many drivers. It's nothing you do in real time, because it takes some computation power. And working means you get around, I don't know, 15, 20 dB difference in between the zones, which is impressive, but it's not like walking in silence and then, hey, I'm here, here's my sound scene, I work out of that's not working.
So I think one of the, we talk about theories and stuff, but I think the part that it makes us, it makes me personally disoriented by this idea of jumping is just this idea of this focused, very defined sound is jumping, right? That makes me feel like a little bit disoriented. If I'm not in a sweet spot.
Mm.
Are there people who works with the idea of not creating this defined focus sound source, but actually working with the diffuse sound, but actually creating this diffuse sound idea
Sure.
as a defined sound source?
That, what I would call traditional glitch music. So you take whatever artifact you can get out of a system and you make music with it.
Glitch hop. It's a music style called glitch hop.
Yeah, glitch hop, for example. So also with wave field synthesis, of course, people like Rama, when he was working at IRCAM, he was trying out things like this. Just saying, okay, could I use it? Does it make sense? Can I control it? Or is it uncontrollable, which could be beautiful as well, to get something which you cannot control. So the phasing is well defined. We could even compute and show you for each point how the phasing looks like, because it's just a linear function and the wave just travels in the room and there is no magic in there. It's linear acoustic, so we are in the easy part of the life. But sure, you can just put all the sources behind the audience and just listen to the artifacts in the room and let them walk around. You get this weird phasing of all sources. That works.
What about motorized systems?
using robotics to control phasing on a,
For what reason? Or how?
well, I don't know, I was thinking of some fixed and some moving so that you could have a more dynamic.
So a robot would just help you to say, if you want to move a sound source to the audience, you move a sound source. You put a speaker on a robot, on a drone, and it's just flying around. For all the rest, what you can do is you can use this, like the Audio Spotlight, this high-frequency ultrasonic speakers, which work like you have a plate with very many ultrasonic speakers. They're very small, so you can put very many on a plate. And then you get a demodulation over the air. That's a natural phenomenon, which demodulates the high frequencies to lower frequencies which are in hearing range. So you get a very, very narrow beam. So it's like lighting.
Yeah, right.
And then you could steer sources around and do such things. That works quite nice.
With a moving head, with a light.
Yeah, it's a moving head with sound, with a very narrow beam. Rather limited in frequency range. It works nicely for voice, for music.
Police uses it a lot.
Yeah. To listen to music.
Marcus, I have a question actually that maybe you can. So, and please correct me if I say incorrect things. So you project a sound out into space, right? We're at a point in the middle of the room where the sound resolves to, right? But it's only a particular frequency range that is actually, that we can use as localization cues, right? Up to, depending on the density, it gets higher and higher, right? But so let's say that's up to, I don't know, 4K, just for argument's sake. So all of the frequencies above that, right, we're not using for localization, correct?
Not using is, of course, your auditory system decides what are the most stable cues.
Yeah.
Because we search for stability somehow. And so there are some things, when you get the first wavefront well done in the low frequencies, then you already get the localization from these directions.
Yeah.
So there are many effects like this. But in horizontal plane, you only need up to 5 kilohertz to be reproduced nicely. Then you get the level difference and the time difference in the ears done right. So you get stable localization. Yeah. But if you just mess everything up above, then there is not a bandpass filter that your ear switches off and say, hey, I don't need above 5 kilohertz. So it's just, creating some other notches and trebles which are permanently interpreted, and you may have some weird artifacts in high frequencies.
Sure. And then when that sound then resolves, and then, like you said, it goes forward, and then hits a wall, and then all of those things reflect back at us, right? Mm-hmm. And so the sounds within that frequency zone that we are using to localize should resolve back to us from the reflection in a way like it was coming from that spot. But what about the other ones? Do they reflect back from that spot as well, or do they reflect back from a more wide?
Everything reflects back.
Yeah.
So the problem is when I move a source very far into the room, then I create a sound field which has many phasing artifacts, which of course bounce off the walls as well. So the original idea of wave fields, because actually we trick physics with the focused sound source. So the original equation which we solve is for sources behind the array, because we play in a source-free volume. And then here, when I play from sources behind the array, I have a perfectly synthesized wavefront just going into the room, which behaves like a natural wavefront. So the acoustics of your room in which you play will behave like with the natural wavefront. But then with the focused sound source, when I'm close to the array, I'm very close. So I have a wavefront which doesn't match perfectly, just in this region, but okay, it's cool. And the farther I get, then it gets very narrow. So let's say I put my source very close to the wall there, then only this beam bounces off the wall, and the rest is the phasing in the room, which is very quickly masked by diffuse sound field, because it's like a diffuse sound field. You have many reflections, you add them, and then you get a lot of phasing. So what we had last year in the concert hall is, because we've been trying it out, to put the source very close to the wall. And then we heard a very clear first reflection. And this was the moment where I was asking myself the question, why? Because it shouldn't work that way. But yes, of course, because I focused the sound energy directly in front of the wall, and it bounces in a very narrow angle It goes to the wall and bounces back. So this worked quite well.
And is it possible to account for that on an acoustic 3D model? Like for the early refractions, absorption, the coefficient of absorption of the walls?
Sure, ideally, so when you want to work with focused sound sources and get rid of these reflection effects, you shouldn't have reflections in the room. But that's a condition we do not have very often. So I think the easiest way is to work artistically. So it's again by listening. So when you work with a system, you listen, you see how it behaves, and then you, like Charel in Le Père, his opera or music theater. So he wanted to project sound into the audience. It didn't work as he wanted, and then they worked with sound grains or sound snippets. Because this works, you don't care. When you're in a sea of sound snippets, you don't care because you don't feel the phasing artifacts. But if you always have some snippets which appear in your ear and they're really here, then somebody's very quickly whispering in your papa. Then it works, and you hear the others just around, so it's like in a grain cloud. And this works quite well. So yeah, you have to produce content and just see what's happening. And of course we can compute everything. Not everything, but...
I see these sound engineers that they come with a microphone and I see in the computers they have a whole acoustic model of the room. They're like, wow, that's pretty impressive. You know, so I wonder if I can compute this OBJ as a 3D object and put it...
What you could do is you could use a microphone array, and then you use the wave field synthesis like beam steering, and you send a beam of sound energy and you scan the room with an acoustic beam. And you recorded the reflections, and then you just get the window out, the time of the direct sound and the early reflections from different walls and whatever. And so it's called acoustic scanning, and so you try to scan acoustically the room.
And getting the acoustic scan together with the wave field synthesis system to work together, is this something already done? Or?
In how you want them to work together?
Like this system to another venue. So you go there and you acoustically scan the new venue, and then you introduce that and you compute a new calibration for the venue. I don't know. That's how we in video art we work. You know, we put the camera, projections, job done, and then we calibrate right away. You know, so I wonder if
you could do some kind of calibration, but you would just use it for calibration in system. That's what sound engineers normally do. When you come to a room, you calibrate the system for the room. But it doesn't make sense to bring a wave field synthesis because I just bring a spherical speaker, which is easier to transport, and I can steer my sound engineer to 360 degrees, and I can scan the room. So in my opinion, I don't see any reason for bringing hundreds of speakers when I can do the same thing with a spherical array.
Do you think we could AV a distance source with the density up and the density low?
Sure. So that's the lower part. Upper part. Lower part. So there's the difference. So I go once back and forth. Upper part. Lower part. And for No, it's more like it's this, but it's not the EQ of the system. It's the spatial blurring which you get, and also you know you go from 6 kilohertz of proper wave field synthesis to 3 kilohertz.
At the same time, I mean, when it's just on the lower rate, it seems louder to me, kind of.
Yes, I do admit that we didn't measure the loudness in the room and do a very proper, you know, we said, hey, we want to show this to people and stick it together.
But somehow the loudness maybe compensates for some of the definition, maybe a little bit.
Maybe a little bit, but so last year we've done it really done well in the concert hall, and it's more than the loudness. It's really because it's also timbre. And if you would go lower and lower now, as you know from your experience with our arrays, then you see that you go from violin to trombone, and then you write the piece for trombone because it's better, because you can play it over the wave feed.
I would say, to me, it's a difference in transparency of the song.
Yeah, it's a clarity which...
The resolution is finer with the closer spacing, and it seems to be more transparent. And so,
Full HD and 4K.
Yeah, no, that's what it is. So we get a smaller pixel size.
Once you get to 4K,
Yeah.
But it's surely also that you doubled the frequency range. I mean, the clarity, you doubled the frequency range. So the clarity, for instance, I really noticed that the attack on the guitar became really clear.
Yeah,
And so I could feel the space around that, which I can't hear in the single.
yeah, because
But that frequency range is
it's
something
source
really
size and frequency range, of course.
Could you not be actually losing energy from cancellation in higher frequencies as well?
Sorry?
Could you actually not be losing energy from the cancellation in the higher frequencies? Or is there some Parsifal's theorem or something?
I'm not sure if I fully understand the question.
Like when you add the higher frequencies, maybe you think like, okay, I have more sound now, so it should be louder. But could you?
No, I do not add any higher frequency. It's always the same sound energy. I do not compensate for whatever. So I get sound in, and the only thing is it reproduced in a frequency range properly? So up to what critical frequency is it reproduced properly? So I have the same sound energy coming with low array, and it reproduces sound field up to 3 kilohertz or whatever. And above, the energy is there, but it's just phased out somewhere.
Sure.
There's an interesting effect though, like, because, you know, we kind of open up the, you know, higher frequency range with actually more definition. It also, the sound pops in, like you feel it's closer. You actually feel the distance.
It's more defined. I would just call, as Johannes was saying, it's the clarity which changes. So here we are rather close to the array as well. So it was a little bit easier to understand in the concert hall last year, because we've been just running around, going to the balconies as far as possible and moving the things around. And when you do very many sources, and then you swap in between the single resolution and double resolution array, it's just, you have the same position, but it just becomes clear, it opens up, it gets fluffier. It's not like blurry before. And the blurry thing also changes the distance perception. So.
I'm sorry to put you on the spot, but could you also demo the orchestra behind, or
Yeah, sure.
Anything with lower fundamentals, like the...
Sure. Which one was this? I have to use maybe less level. So we start with the lower part. Thanks for mixing. Okay.
Can you give a word about the technical challenges? The
Okay.
engineering challenges of making a W, or like, bringing the second array in physically? Do you have an idea of that? Have you thought about that already?
No, the engineering challenge, I'm not a speaker manufacturer. You just have to make the housing. Of course, you could create it like this, like to make a double house case and just being well separated. So it's not a huge challenge. It's just you have to redo everything. That's the main challenge of cabling. But of course, we've been getting into discussion last time. It's a very well-sounding array, and there's a lot of engineering thoughts in there by Todd, who worked a lot on trial and error, but also on computing the Thiele small parameters. So it was not just fishing in the blind, but of course, you may have other ideas. When you manufacture a speaker, you do the bass reflex or whatever, it's a whole engineering thing. So many speaker manufacturers, high-quality speaker manufacturer will come and say, no, you should do it that way and that way and that way. Yes, do it, please. I think, but yes.
Yeah, so this is only the prototype, and we just never thought about actually inverting it and having the distance. And so there is a little bit of an irregularity because of how the boxes are built. So the idea is, if there is ever a second generation, to actually build it very precisely so you can place the top one inverted on top of the other one. And I don't know, I wasn't here at the beginning. Did you also play it like with a 10 centimeter distance?
Yes, we did, yeah.
Okay, so I think we discussed this and we just said, once we had all these modular arrays, well, let's see if it works if we space them in the zigzag line. And as you can hear, you can hear a difference. So the next generation would be designed in a way that it really aligns properly.
So the idea was more, when we've been talking about this project, I was saying, yeah, get the smallest and most efficient speakers you get and then put them in a line, because that's what we can do. And then we came up with this 5 centimeter spacing. I said, hey, cool, 5 centimeter spacing I was thinking that's fairly enough. And then when I was here for the 5-week period, we came up with the idea, hey, wouldn't it be cool just to listen to it? So I was computing the filters, they've been setting up the array that way, and then we did a little bit A and B, and then it is clear it makes sense. So if we turn time a couple of years back, and Johannes would come now and say, what should we do? Should we build an array and whatever? I would say, yeah, let's do a W-shaped array and reduce the spacing. And maybe if I come next time, we put 2 on top of this and reduce it. No, they start hating me.
Is there a name for it? Like I have a Wakefield system with 6K resolution. I understand it goes from 700 to 6K.
No, maybe we should once start like in video, yes, to use 6K or whatever. But no, it's just a high-density loudspeaker array. And by the way, you have very many loudspeakers. You can use other algorithms than wave feed synthesis. With that resolution, you can do beautiful beam steering. You can just say, hey, steer a beam, and do like scanning of the room or whatever. So you have just a very high resolution array, which allows you to implement things like a well-synthesized focused sound source, which is only possible with a high resolution array.
We can't go much higher because you cannot really localize sources above 10K, I guess.
You can localize sources in elevation above 10, but it's the primary Q, so up to 10, yeah.
So the idea in building this system, as I said 2 days ago, was actually, is there an auditory difference? Math tells us there's a difference, and I only listened to systems which were this far apart, or this far apart, and does it make a difference? and that's all. And it does make a difference, as we
Yes.
can just hear. And then out of that comes the next consequence, like Bobby will talk about the artistic application. And then you could also think about the scientific implication. And the only idea that motivated building the system was to say that the localization cues are above the 1.6 kilohertz, which most systems did. And I said that cannot be true. Let's build a system where we actually can reproduce the localization cues with the right wavefield, so it reaches us in the coherent wavefield way and not just scattered all over. And that was, and all what we are hearing now, that you can do the A-B comparison between 10 centimeters and 5 or 6 and 2.5 or 3 is just the proof that our perception still beats mathematics, and that we can actually hear the difference.
No, also mathematics says that the difference is there. So
Our perception confirms that.
the perception confirms, and it's more that you see it makes sense, because very often, from a mathematical standpoint, I would just say, no, that's not enough. I want to go to 20 kilohertz, so I need a spacing which is, very small, and I need a wall of speakers, and then we do real wave field. But
I think there's a really interesting potential that was revealed to me by the switch between the 5 and the 2.5 centimeter. Is that at the 5 centimeter, it's almost like the kinds of decisions you make in a Tonmeister sense of like, do I want coincident XY at 7 meters, or do I want ORTF or at 9 or whatever? And as you do that, you're changing the spread and the blend between the instruments, and you're changing the soundscape within a stereo field. That's an artistic decision that a mix engineer or Tonmeister makes as they're doing a recording. And I think there's a wonderful potential for creative sound diffusion separate from the artistic sense, that you can start to think with a high enough resolved array about the amount of width of a sound object occupying the sound field as a creative decision that's on purpose, where like I want a 4-foot bassoon and a very highly resolved flute, which are the kinds of things that when you're mixing a rock record or you're mixing a classical record, you're trying to make a decision about how you want to place items in the sound field and where they fit in the depth of the field. And this just allows you to do that in the performative situation, and that's a really rich potential, because it opens up all of these. The tracking engineer and the mixing engineer are now part of the performance of the system, not just the capture and reproduction of the system, which is a really interesting potential.
Because just extending on that, like for me, the recording of the bassoon is too close. The microphone's too close to the bassoon. I can hear things in the bassoon I wouldn't hear if I was in the audio track. And that made me think, well, what if the recording of the bassoon was an ambisonic recording, and then we could actually move the virtual microphone back from the instrument a little bit. And it seemed to me, just thinking about this, that combining those would be quite interesting, to be able to change the proximity to the instrument.
it's less the idea of having an ambisonics microphone, because you don't want to capture the room, so does in this make a little bit less sense, but getting more microphones set up and mixing a proper signal, which just, when your microphone with one microphone, you get part of the instruments.
Sure.
And so getting more microphones set up and recording it properly, and then make a monophonic mix out of this, which you project, which would help.
But you could just use a beam, right, and move it.
You could use a beam, yeah.
From the source, which would allow you in the mix to choose how close you wanted to.
Yeah, that's true. That's true.
And I was thinking, with the combination of what you're doing now, that would be super interesting to be able to change the distance from the instrument and the resolution at the same time. Because as you go up, obviously, you're getting all these cues in the extra 3K. That means that maybe you want to step back from the instrument a tiny bit, and you could actually play with adjusting how much that was.
I actually one comment about that, sorry. What you are saying, because in the first day when we were, experimenting with microphone choices arrays, when we opened up the room microphones, we heard the closed microphone and we opened up the room microphone at some point. And I think it's actually really made me feel like, again, oriented, again, like stable. So I wonder about the same question, like we are trying to, I understand the purpose of getting a mono source, getting close source, whatever, but I also wonder if eliminating all the cues, maybe we are kind of.
No, the only thing we want to eliminate is the room.
Well.
I don't want to
right.
have room information or crosstalk in between instruments, because then it doesn't work anymore. So if I have, so you can use it in an artistic way to get a reverberated source in there. It sounds funny, or funny, however attractive you want to give it, or you know. But just in terms of sound engineering, when you want to reproduce an ensemble piece with wave field, for example, if this is the goal, then you should get a very clear recording which captures all the frequency ranges of the instruments, which you normally, without any room information.
Well, I don't know. I think there's, you know, as a sound engineer, I always like to actually put room in a room in some ways. So
Yeah, but you're not putting room in a room, you're putting room in a source.
Yeah, room in source, but
Yes,
I mean,
but
just
it's
mathematically, you can do whatever you want if you have the basis elements. So it seems like, you know, if you can separate out, if you can decompose into orthogonal elements, you can build whatever you would like. But it seems like the problem is that to do like real absorbing boundary is too you need like another one of these with all like, I mean, you'd need so many speakers, right? And so fine to do, no?
I don't
think the issue,
get
and this is where it's super messy, is that instruments were designed to excite acoustic spaces. And when you take them out of acoustic spaces, they behave different. And when they behave different, they don't sound correct. And so when we close mic them and we take them out of rooms and isolate them, we make an artificial thing that the ear hears as artificial because we're very subtle, as we've just learned. And so I think you either have to compute enough room to give the instrument enough time to bloom, but you have to then capture the instrument in a way that captures it where you can have the bloom.
Because the instrument itself is an acoustic space as well.
Yeah.
The body of the instrument, like it's one of the things that Garth was saying is you got a close miking of a bassoon and you make your clickings or something like that, or if I think like a string instrument, you hear articulation noise. And so even if that source moves away, you're hearing the articulation noise, what you think of as unnaturally loudly.
But the thing is that you don't, it's because you're playing it back at a different level. If you were to actually sample, if you had a bassoon and you had, you know, an infinite number of microphones surrounding the instrument and all you know, capturing its full radiation pattern, all frequency range, you want as many details as you can get so that when you play it back, you can do it in a realistic way. If you're only taking one microphone, then you have this much limited.
But then, of course,
you want more detail, not less.
You still suffer, just in a second, Johannes, you still suffer from the problem. You reproduce a point source. A piano is not a point source. So, you know, it's a whole, but yeah, that's the fun part now. We provide the technology. And now you have computer musicians who have special needs, you have sound engineers who want, but we have to redevelop what we know up to now on sound engineering, because even when you work with an Eigenmic and you do a recording with a 3-dimensional 360 degree or however I never know how you should call them, 360 or 3-dimensional. So Jens is here, call it Eigenmic. So we did very many recordings with the Eigenmic, and then the main problem is, on the one hand, it's very close to what you do with main microphone and spot microphones. So you don't change everything, but it's not anymore a stereo image or 5.1 image you're mixing. And then when you get into VR, and then you can move around the scene and whatever, so you really find a little bit the art of sound engineering, which I think is beautiful because it's a nice challenge also for sound engineers. So Johannes, you had a...
So just to, again, come to the why did we do the recording of the wind octet and the string quartet? So the intention was not to build a system which would reproduce traditional music in an even better way. It's fine if it does it. So the first time I listened to a Wavefield system was in Germany in 2000, the original system from the Netherlands. And I was totally upset about all these tonmeisters who try to recreate a concert hall. I said, what the hell? Go to a concert and sit in the concert hall. So the idea here was to build a system, and that's why it's modular. You can place it anywhere in the space. You can put it here, you can put a window there, to actually see what we can do with it as an instrument and not as a reproductive organ. So the
That was a good.
So, and why we did the recording with the string quartet and with the octet was actually that we have a frame of reference from what we know in the real world to be able to evaluate it. Because if you use only electronic sounds or acousmatic music, there is no original we can compare it to, because it's always its shaped entity in timbre, in frequency, and what it sounds like. But by verifying it with like the wind octet, we can say it works better. And so after the string quartet, we chose a wind octet because the transients of wind instruments give you the spatial cues. So that it was a very conscious decision, because the bow noise is different from the transient of wind instruments. And so we said, okay, let's take this octet recording, and we were happy to get the money to hire the musicians and do the recording. And then if that works, if that tells us the difference between the single array, the W shape, then now we can use it to create music, sound, which we could not create otherwise. So that was basically more the kind of impact direction of going about it. Let's develop a tool with which we can do which we cannot do otherwise, but we verify it basically like in the old days with analysis, resynthesis, and say, okay, it matches, it works. We can rely on our verification through perception, and now we can open it up for instance, what Barry will talk about.
Okay, I think it's time to get your lunch.